I've chosen a few examples in artificial intelligence to tell you about. But first, I'm just starting with this beautiful night sky from Hawaii. Astronomers have found thousands of planets orbiting stars other than the sun, and we call them exoplanets. So for my talk today, I'm going to give you an introduction. My instructions were that everyone should be able to understand the introduction. I'm going to give you some examples in exoplanet discovery, characterization, and at the end, I will talk to you about the search for life on other planets by way of gases in the atmosphere. Now, at the outset, I had AI in my title, not deep learning, and I'm considering like AI this umbrella term for all of these different types of like machine learning, representation learning, deep learning, because in exoplanets, although people really are using a lot of examples of AI, deep learning hasn't really got a foothold like we'd want it to. So that's why I don't have a lot of examples of deep learning. At the outset, I'd like to add that in exoplanets, people want to grasp onto AI as a tool. We don't typically have, I can't really speak for everyone in the field, but people typically don't have the sort of, maybe let's say, interest or technical ability to understand it at the deepest level. And so usually we find a colleague, and we want it as a tool mostly for efficiency. And I'm hoping, though, that someday we'll use deep learning and that it can somehow unveil for us like some deeper physical properties or hidden properties that we weren't really able to find any other way. I really hope that eventually deep learning will do that for us. So for part of my introduction, I want to start with this little video showing you a fake map of our galaxy, and it quickly zooms in to what is a real map of our sky. Each one of the points that you see in white and colored is actually a star, and the highlighted stars are stars with known planets. And it's supposed to give you like a sense of just how many stars with planets there are. Each color of star represents a kind of a different type of star. Now you can zoom in, you can get this software and zoom in. Here it's choosing a location on Earth that is from California. And in the spring night sky, this is what you could see. You'd need a telescope though. There's, by the way, a very special patch of the sky. I know some of you know what this is, but there's a telescope called the Kepler Space Telescope that focused on one part of the sky for 4 years, and it found thousands of planets. Now, the software, you could actually type in a name of a planet if you know one. It'll zoom in to the real location of the sky where that star with the planetary system is. This particular one is Kepler 186, and it's got, let's see, 1, 2, 3, 4, 5 planets. And it actually, you could ask yourself, one of these planets is in the zone around the star, whereas heated by the star, the planet would be not too hot, not too cold, but just right for life. So our night sky is just littered with stars with planets. Now here you have to, it zooms in, and you'd have to read that fine print. Hypothetical visualization of planet. So in this case, we don't have any data like that, actually. In fact, we don't have a lot of data at all on these stars with planets. Mostly we know that the planets are there, and we will know something about their orbital properties. So continuing on my introduction, we just like to tabulate all of the known planets, and here's a kind of subset of them. On a graph that I want to emphasize is a log-log plot. So you can see planet size going from Earth is just normalized to 1, so Earth size, up to 10 to 20 times the size of Earth. So Neptune is here, Earth is here, Jupiter is here. And all of these points are known planets. Each color and shape is a different planet finding technique, which I won't go into detail on. I mostly just wanted you to see that, wow, there's so many planets, and they really span nearly all properties that are possible. For example, there are planets that are so close to their star, 100 times closer than our Earth is to our sun. And based on Kepler's third law, these planets would orbit in less than a day. And they're so hot, the surface is hot enough to melt rock. On the other extreme, we have planets that are so big, they're like inflated. They're bigger than Jupiter, and physics can't really explain why. So we have planets everywhere, and it's fair to say that in the dark part of the diagram, it's dark because our technology can't reach there yet. There's selection effects that prevent us from getting to planets really far from the star or really small. Now, I wanted to add one thing. Don't like overanalyze this plot for patterns and things like that, because we haven't done, in exoplanets, we're still just very busy finding things. We don't really have completeness down in terms of our surveys. And also to make this plot, I had to fudge a bunch of things because many planets are measured in terms of mass, not radius. And so to convert it, you have to invoke some kind of somewhat empirical fudged way of converting. So that's where we're right now. And to learn more about planets, which I'm going to get to later in my talk, we'd like to be able to study the atmospheres. And I've highlighted with circles now the planets, most of the planets that have had their atmospheres studied. So you can see it's just a subset of them. But I want to just point out at the outset that atmosphere really matters. So in the future, when our technology lets us study planets like Venus and Earth, to any planet-finding technique we have available to us, they look the same. They're about the same size and the same mass. But if you can see the atmosphere and learn about the planet and infer something about its temperature, we would know that Venus is so hot, and way too hot for life, way too hot for water, whereas Earth is very clement and habitable. So going back to the different techniques, they're based on like size or mass or brightness. And I'll ask you for a moment, if you were going to change fields and go into planet finding, which technique would you use? Would you use one that involves size? Because our own Earth is about 100 times smaller than our sun. Would you do mass, a technique based on planet finding based on mass? Because the problem is that the planet alone might not be so hard to spot, but it's right next to a big, massive, hot object, the host star. So it's dwarfed by the star in every sense. Or would you do something about mass, because it's 300,000 times less massive? Or would you go for gold and try to work on brightness, a method involving brightness, where the Earth is 10 billion times fainter than our sun? So I don't know what you would do. Me, I'll do the last one, which I won't have time to talk about unless you ask during the questions. But the most common way to find planets now is by size. Most planets are found that way, and that's how they're studied, because it's the easiest thing to do. And here's a little animation for those that aren't familiar with it, showing you a planet. Can you see the planet here? It's supposed to be about Earth size, and this is like a fake image because we haven't spatially resolved any stars other than our sun like this. And here's what the astronomer measures. You're measuring the brightness of the star as a function of time. And the planet covers part of the star, and it drops in a tiny amount of brightness. And in fact, for an Earth-Sun twin, it's actually a part in 10,000, not a part in 100. So it's not quite as easy as I said, because it's an area ratio. So you have to square to get that. And that's basically how we find planets today. Look at lots of stars at once, looking for this characteristic drop in brightness. By the way, though, any noise in your system can easily look like a transit, because if you have a little shift, you can get a drop or a rise. And so there's riddled with false positives and other things. Now in exoplanets, we're doing one more thing to make it even easier. And that is much of the field is funneling towards finding planets around very small stars. So here's a scale image, a real image of our sun with this fake planet, and a fake image of a tiny star with the same fake planet. And look how much more area the planet takes out of the small star than the big star. So the drop in brightness is a part in 100 instead of a part in 10,000. And finding planets around small stars is easier for many, many reasons. One more is the probability to transit. The closer the planet is to the star. I forgot to mention that for a planet to go in front of the star, it has to be aligned really just so. But planets' orbital planes are randomly distributed. So if you have the star and the planets orbiting the plane, it would never transit. It has to be lined up just so. And this probability to transit, that it's lined up from our viewpoint, the closer the planet is to the star, the higher it is. So to find a true Earth twin, it really doesn't work out for transits. Probability is low. The atmosphere compared to the backdrop of the star is tiny. And so that's where the focus is now. That concludes my introduction. And now I'm going to move on to exoplanet discovery. And the field of exoplanets is so huge. So I had to pick and choose kind of hot topics and a combination of hot topics and things that I work on. So right now, there's a big thing happening in exoplanets. It's a satellite called TESS, Transiting Exoplanet Survey Satellite. It's an MIT-led NASA mission. It covers nearly the whole sky. And it's looking for these tiny drops in brightness due to fortuitously aligned planets that happen to go in front of the star as seen from the telescope. I'm not going to go too much on the details of what it is right now, but I just want you to see that it essentially has 4 identical cameras. These are giant baffles, so it makes the camera look a lot bigger than it is. The lenses are only about this big, 10 centimeters across, because it's aiming to look at bright nearby stars. And they have these giant baffles to block out light from the Earth and Moon. And so, yeah, TESS is lots and lots of people working on TESS. Yeah. Here's a picture of it for scale. This was about a year ago while it was still being put together in a clean room at Northrop Grumman. And you can see the size of the person compared to the size of this spacecraft. And there are the lenses. They have covers on them which are taken off before launch. The only deployable is these solar panels. Here's the antenna that communicates with Earth. And it really has nothing super special about it, actually. It's just the cameras are like made as perfectly as possible. But other than that, nothing was, even though this is a very expensive mission, like risk can be bought down if there's nothing totally new. Well, a bunch of us in this room got to go to the launch last April. And it launched on a SpaceX Falcon 9 rocket out of Cape Canaveral, and it was like a beautiful day, and it was just absolutely stunning. And some of us, like me, unfortunately was 6 miles from the site, so like it was like that big, like a toothpick, but it still looked great, and the plume was just incredibly bright. So on this rocket here, all of this, the test fits in this spacecraft like smaller than this point of light in the top of this fairing. And TESS got launched into a very unusual orbit, where it takes almost 2 weeks to go around the Earth in a highly inclined, highly elliptical orbit. And here's a picture of stars. As part of commissioning early on, it just snapped this image like as a kind of beauty shot to show you some pretty stars in the picture. Now, TESS has a very, very wide field of view. It's trying to look at lots and lots of stars at one time. So that image fits into a tiny part of one camera. This is, remember I said there's 4 identical cameras? This is like one camera, and it's got 4 detectors, and that was just like a little patch of one of them. So each of these cameras, the whole constellation of Orion could fit within a camera. Actually, I'm getting to some machine learning in a minute, and so each of the cameras is organized in such a way that it takes up one strip of the sky, like this. So TESS is looking at one strip of the sky for 1 month, and then it's rotating around the southern hemisphere first, and then the northern hemisphere. So our goal would be to find planet candidates out of all of these stars. And let's see. I actually just made this little menu for you. And I know that those of you here who do work in deep learning, please don't laugh at this part of the talk. So it's kind of a very manual process right now, especially when your data is new to you. You really want to look through it and understand the idiosyncrasies. So essentially, we have all these stars here. And in the full frame images, we basically do identify stars with a catalog down to some brightness limit, and that'd be about 500,000 stars of interest per sector. So 500,000 stars for one of those big strips. And essentially, we detrend the data. By the way, people detrend without carrying the physical cause of the systematics. Just let our computer fit like polynomials and stuff and remove big wiggles due to either temperature variations or variability in the star. Then we phase fold the data, like at every single phase, loop through every phase possible, looking for a signal that would show this drop in brightness, like the one I showed you in the animation. Then after the computer, so out of those millions and millions of stars, about, let's say, 5,000 would pass a simple test that there's a drop in brightness that passes the dictated threshold. And after that, we'll look at them and do some other cuts, eventually getting down to a few hundred of them that we send to humans. We train, like any of you here could be trained if you wanted to, train people to look through the metrics to decide whether this thing is a planet candidate or some other kind of false positive. And if it's a planet candidate, it gets on a special list and it gets farmed out to hundreds, if not up to like several hundred people around the globe who do follow-up observations using telescopes on the ground to further make sure it's a planet and not some kind of false positive. So I'm not sure if I have time to explain all this, but I wanted to, just setting up to show you if you were going to be vetting, and people are literally doing that as we speak at MIT. We have some new data we're working on. You'd get this plot. So this is like a little snapshot of some of the metrics that humans will use. First of all, I want you to look up here to the cleaned up detrended data. And do you see all the drops in brightness? They're conveniently, this is all automatically made by the computer. Do you see them? You have to see them because they're conveniently shown to you by a little blue triangle. And when the data is all face folded, the computer spits out these two here. And you see the drop in brightness? Yeah. So what you see here, actually, that would tell the vetter, it's not a planet. Because look at how each alternating transit is a different size. So it's not due to a single object. There are 2 objects eclipsing each other. One is bigger, one is smaller. One is creating a small drop in brightness, one is creating a bigger drop in brightness. And so we actually kind of work through each of these boxes, which I don't have time to explain. And the human will then check off one of these. We literally have this software we spent a lot of time developing. And you would click off an option here, like planet candidate, instrument systematic, binary star, variability in the star, or some other thing. And eventually, those that are resolved by consensus are done. And if there's some confusion and the 3 people doing this don't agree on it, it goes to like a group setting where then a group of experts meets and sort of figures it all out. So that's what we do. I have a couple more to show you that aren't as obvious. So this is the cleaned up time series. And by the way, this is like about a month worth of data if you count the days on the bottom. Here's where the spacecraft is downlinking data to Earth, so it's not taking data. Do you see the drop in brightness here? There's a little, by eye, you can see that. Here's where something went wrong with the pointing of the telescope. And now here's the phase folded stretched out. Now this one looks more like the animation I showed you, a drop in brightness, somewhat small, corresponding hopefully to a planet candidate. And there's a bunch of other metrics I can't get into right now. So this one would probably be labeled as a planet candidate and move on. But it actually gets much harder. Most of the data doesn't look like the ones I just showed you. It mostly looks like this one. Now look at this. Do you see a drop in brightness on the top? It's a pretty small thing here. Look at this. Here's the phase folded data. It doesn't look very good. Look at that. So the computer thinks this looks like a transit. Kind of does. But our other metrics, which I didn't have time to explain, they're not working out for us. This is just a jumbled mess. This is supposed to show you that the catalog, the star you've associated with, isn't the brightest source in the field, and et cetera. So we literally look through these, and the experts just page through it. It's like you're sort of just randomly looking at them and deciding what it is and farming it out. And that's kind of where we're at right now. So summary, we see these transit-like signals that pass a threshold. They go to this team of humans that are vetted by humans, or algorithms can also sort through the metrics that we have the computer assign. The best signals are passed on for further follow-up observation. Human vetting is time-intensive, okay? It's so intensive. Although the best people can get through like a couple hundred of these in a couple of hours. But then we have this group setting, and there's lots of people involved, and it really is time-consuming. Also, it can lead to biases in the signals selected, particularly marginal signals. Ground-based surveys that aren't in space, they have bigger problems because they have a day-night problem. It's daytime, they're not collecting data. Weather's really bad, and it really affects your duty cycle. And there's lots of noise from our atmosphere alone. The positive in all of this, manual labor, which is sort of it's like opposite of this conference, right? Humans like pouring through data. The good news is we end up getting a well-labeled data set. But it's not enough. It's not like tens of thousands of objects. It's maybe, right now, after a few sectors, we have maybe like 2,000 objects that are well-labeled. So there's a lot of work going on in the field where astronomers are kind of grasping to try to use artificial intelligence solutions. And this slide's a little crowded, so I'll walk you through it. But I wanted to list just literally a fraction of the attempts to automate vetting. And people like to use random forests and self-organizing maps or clustering based on light curve shapes. And here, people are simply using machine learning as a very fancy classification tool. One of the problems we face is we don't have enough training data here. Because we don't have enough, thousands of planets sounds like a lot to an astronomer, but to machine learning, deep learning, it's not enough data. You could say, why don't we use simulated data? We can, but it turns out when you inject a fake transit signal, that drop in brightness, it never, ever, ever matches the real signal. What people have to do is more complicated that they're not really doing. They have to go back to the image level and inject the signal right at the image level, not just put in like a shape after the processed data light curve. There's one case that got a lot of attention using deep learning, deep convolution neural network. It led to a team, actually there was someone from Google involved, because remember how I said astronomers usually get someone who works on the field? And in this case, they actually were able to sift through lots of data, way more data than the humans could vet, and many more marginal signals. And they found this planet here, little transit, hours from mid-transit, so last a few hours. I want you to look at this scale here. Like if you work in any field of science, you never work at things, I'm sure, unless you work on like, we don't have our person here who works on gravitational waves, but in most fields, you're not going to this many decimal places. It's a tiny, tiny signal. And they were able to dig this signal out of the data. And it turns out it got a lot of attention because it's an 8th planet around a star called Kepler 90. It's now in a tie with our sun as having the most planets known. So in the paper where they made this discovery, there were a couple interesting things. They had only 15,000 labeled data as training, and they have to divide that up. They have 15,000 labeled data, which they had to divide up into training and testing. And so they really need to start using unlabeled data. That's where our opportunity lies in this field, is we've got to sort of branch out to get more and more data, more and more data. The other interesting thing that I've seen a lot of when I've been reading papers in preparation for this meeting, that most of our AI efforts, unfortunately, they don't match the more mature kind of brute force methods. So when I was showing you all those plots, it turns out that we can use, there's this, we have things based for Kepler data called RoboVetter or AutoVetter, and they do just what the humans do. They look at the same metrics, but the computer figures out whether it's a planet candidate or not. And those ones still outperform the AI methods. So we have room here in the future. It's an opportunity because there's tons of data. It's not an inverse problem, and it may not involve deep learning, but we have to learn patterns on the unfolded time series. We have tons of data. There's, in each of those sectors, millions and millions of objects. There's lots of science beyond transits. And I think there's a real opportunity here to do better. So we want to find planets. Once we found them, what are we going to do? We'd like to characterize their atmospheres to learn more about the planet. So for example, and I'm actually going to tell you a little story now about the small stars, because we're just sort of gung-ho on finding planets. We want more and more planets, and we're working to do the easiest thing first, but we're not always sure if it's the best thing. So the planets orbiting the small stars, I'm going to explain it to you, not with like complicated computer models yet, but I want to take you on a virtual trip to a planet orbiting a small star. Now, depending on the star, imagine we could get in a spacecraft and like travel to the star. Depending on the star, it might be very big in the sky, because these red dwarf stars, they give off very low luminosity. And so for this planet to be the right temperature for life to survive, that is for us to visit, the planet has to be quite close to the star. This artist here who made this picture used an artist's license to make the sky red instead of blue. It turns out that most planets appear to have some kind of clouds or haze, and we're not really necessarily sure why or what the properties are. One interesting thing, if we were to visit this planet, is the planet is tidally locked. That is, it rotates one time for every time it orbits. It shows the same face to the star, just like the moon does to Earth, because tides over time have made the planet want to go in its lowest energy state. And unless there's another planet around or something strange, we're literally convinced that within tens of millions of years, the planet would reach this state. What this means, if we could visit the planet, is the star or the sun would be in the same place in the sky at all times. So you could visit where it's always daytime, or the astronomers would go to where it's always nighttime. Now, these planets orbit the star very quickly because they're very close to the star based on Kepler's third law. And so what this means is that the year would be very short. Your year could be only about 10 days or so. So a lot of the properties, basic properties on these planets is very different to those on our sun, our planet. Now, in second effect, visiting this planet may not be a great idea. The stars give off flares, big flares, some of them constantly. So you couldn't just flip out your phone and be glued to it, because these high energy particles would destroy the electronics. Like, what kind of sunscreen would you bring? We're not sure if life could survive on the surface, like receiving all this horrible radiation. On the other hand, this strong radiation may be needed to jumpstart life. It turns out that I wanted to tell you a bit about one of these planets, which I think we may hear more about later tomorrow from Julian DeWitt, is that there's this planet called star called TRAPPIST-1, a really small M-dwarf star. And it happened to be in the Space Telescope Kepler's field of view when it looked at one patch of the sky for 80 days. And during this 80 days, astronomers counted 40 flares. And one of these flares was gigantic. It was, they extrapolate, as big as an event that happened here on Earth called the Carrington Event. How many of you have heard of the Carrington Event? This happened in around the 1850s when a UK astronomer, an amateur astronomer, was looking at the star, our sun, trying to understand sunspots. And he saw some of the sunspots literally brighten. And a day and a half later, our Earth became electrified. People could see northern and southern lights all the way down to the equator. Telegraph operators, because that's what we had back then, they took the batteries out and the telegraph still operated. Some of them caught on fire. Our whole Earth became electrified. Now, back then, people didn't really understand the connection between the sun and magnetism on Earth. Maxwell's equations weren't really articulated. And what had happened was a part of our sun had literally come off in a coronal mass ejection, and it had hurtled towards Earth. And this part of the sun had a magnetic field embedded in it, so it hit our magnetic field and induced a current. Now, on TRAPPIST-1 star, they claim that one of the events in 80 days was literally like as huge as this particular event. And some of the stars flare even more. So on the second hand, it may not be so great to visit one of these M-dwarf stars because it could be like literally detrimental to us. And just as a little aside, here in the US, we're really worried about another Carrington level event because this time we're way more sophisticated. We have a power grid that is really susceptible. If that happens, our whole planet will be knocked off. So we don't really know. I just gave you this extreme negative about red M-dwarf stars. I don't know if it's true, but astronomers go really back and forth We don't know like if they have atmospheres. Maybe the atmospheres have been blown off by winds and high energy particles. We really don't understand what's on these small worlds, and so we wanted to learn more about them. And one way to do this is to try to study their atmospheres. So now I'm going to get into tell you a bit about atmospheres, and this sort of next section of my talk is the most complicated part, where I will get to an inverse problem. So here I'm showing you again this transit simulation, but it turns out this artist's conception is showing you that the atmosphere around this artist's conception here is glowing. And it's supposed to convey to you that when a planet goes in front of the starlight shines through the atmosphere. And we actually can pick up signals in the atmosphere as the starlight is shining through. We can measure the star by itself, and we can measure the star and planet during transit and subtract, and voila. But it's not as easy as that because the atmosphere is very small. It's like the skin of an onion on an onion. And this method has now been extremely successful. Dozens and dozens of planets have been observed or attempted to be observed this way. You can ignore that equation. And just backing up for those of you who don't study spectroscopy, I picked up this like Wikipedia level plot, and it's showing you wavelength in microns. This is visible, this is infrared, and it's showing you from 0 to 1 absorptivity. And it's showing you for some different molecules, water, carbon dioxide, oxygen, ozone, nitrous oxide, methane. And it's supposed to show you that different molecules have a different fingerprint. Because of quantum mechanics and the masses of atoms on each molecule is different, they rotate and vibrate and they absorb light differently. So on the whole, you can see water is actually our strongest greenhouse gas on Earth. It has so many absorption peaks. Now, it turns out that the Hubble Space Telescope, which we use for exoplanet atmospheres, though it wasn't purposely designed for that, there's this one peak here, one range here, tiny range between 1.1.7 microns, where this special camera on Hubble that wasn't designed for exoplanets just works exquisitely. And it just happens to cover this one peak here. And there's one thing I forgot to mention, actually, so I've got to back up here. Now, we're going to think about this atmosphere here. And as the starlight goes through the atmosphere, it gets exponentially attenuated by anything absorbing. Now, here's a tricky concept that I'd really like you to be able to walk away with, that what we're looking for to study the atmosphere, we look at the planet at different wavelengths. And at wavelengths where the planet is transparent, if the atmosphere is not absorbing in between a spectral feature, the planet is a certain size. If we can look at a wavelength where the atmosphere is strongly absorbing, like right in the middle of one of those water absorption peaks, the planet looks a tiny bit bigger. So if there's no atmosphere absorbing at a certain wavelength, the planet is, let's say, the size of this opaque region. If the planet is absorbing at a certain wavelength, then the atmosphere blocks the light from the star, and the planet looks a tiny bit bigger. And that's the concept behind studying atmospheres, is we're looking for the transit, the drop in brightness at different wavelengths, looking for a tiny, tiny, tiny change in size if the atmosphere comes into play. So we have this one feature here. And in an exoplanet atmosphere observed by Hubble, here's the feature. This is wavelength in microns. Black is data from Hubble. The red and blue are models. You can ignore these points here. This is showing you the transit size. So it's tiny change. Look, 0.145, 0.146. It's just fractions of a percent, tiny fractions of a percent. And you see this rise in brightness here that matches up with water vapor. Now, all you have to do here is agree with me that these points make something that's different from a straight line. Because if it was a straight line, there'd be no absorption at different wavelengths. And we wouldn't be seeing the effects of an atmosphere. The fact that the planet looks a tiny bit bigger and the atmosphere is absorbing right where there's water vapor, it tells us there's water vapor in a planet atmosphere. And there's many, many, many planets that have been observed this way. By the way, they're mostly hot planets. They're big, their atmospheres are puffy because of the temperature and that they're filled with hydrogen. They're much more easy to observe. And that's kind of where the field is right now. I have this other one to show you. Again, different from a straight line. And again, transit depth in just a tiny fraction of a percent. This is wavelength in microns. The points are data. The curves are some best fit models. And look at this giant feature here. I just want you to sit on this for a moment because this is literally the best data we have in this field. So if you work in an experimental field, my guess is that this doesn't look that great to you. But in the field of exoplanet atmospheres, it's just so hard to get this data, tiny fractions of percent, that we're very, as a community, really proud of these achievements. So I don't know if I've convinced you that there's water in this atmosphere. This is a hot, giant planet. It doesn't have oceans or anything. It has hydrogen, it has oxygen, so water will exist just from equilibrium chemistry. But we'd like to do more ultimately. We want to know how much water is in this planet. We'd like to know how much oxygen compared to other elements, like carbon or like hydrogen, because we want to understand maybe something about where and how this planet formed. Did it get bombarded by like asteroids or heavier elements than hydrogen, or what happened to it? So to do this, we need models, actually. And here's where I'm going to get to our inverse problem. And my next few slides are somewhat complicated, so I'll try to walk you through them. I won't be able to like tell you about all, this is like a semester class, but we have essentially a set of equations to understand our atmosphere. And I'm thinking of a one-dimensional plane parallel atmosphere, just like a column through an atmosphere. We have energy transport, which is typically by radiation. And that's covered by this term I, which is, it's radiation, it's a beam of traveling photons in a given direction. We have conservation of energy, because energy in every layer of the atmosphere must be conserved. No new energy is created or destroyed. We can have transport by radiation. We can also have transport by convection, so that's mass motions in the atmosphere, so we've got to put those two together. We have hydrostatic equilibrium. It's why our atmosphere doesn't collapse. Pressure of the atmosphere balances the pressure gradient of our atmosphere balances gravity. We have the ideal gas law, which is a bit redundant because it pretty much always holds in an atmosphere. Then we have chemical equilibrium, and we have a series of equations literally for every, I want to say, element or molecule. And so if you had hundreds of molecules in your atmosphere, you've got hundreds of more equations, but they're kind of all treated the same way. So we sort of have this, the only thing we actually measure, by the way, is we measure the radiation coming out of the top of the atmosphere. So we have a series of equations. We have the intensity, the radiation at the top of the atmosphere. We want to derive intensity, temperature, pressure, density, chemical composition, ideally at every single altitude. And so here we find ourselves with an inverse problem. Given a measurement or a series of measurements, that's the previous slide, we have radiation as a function of wavelength. That depends on the state of the atmosphere in a known way. And we want to deduce the best estimate of the state of the atmosphere. So this is our inverse problem. Now there's two distinct problems. There's the inverse problem, which in this particular case, there actually is no unique solution. You could say it's kind of an ill-posed problem. One thing I didn't show you, by the way, is in this term here, when we're talking about energy transport, these terms are just like absorbers or scatterers. If you want to think about scattering in the atmosphere, you have photons that hit a particle, and they will scatter in all directions, but not equally. It depends on the particle. So buried in here is literally an integral across this value I. And you have an integral differential equation. You have a nonlinear equation. So we can't invert this directly. And there's this fundamental degeneracy in atmospheres because there's some components that contribute very little to the state of the atmosphere. And so if you're inverting, those quantities could literally have an infinite range. We have a bigger problem in exoplanets, and that is that most things we don't know at all. We have clouds in the planets, but we don't know what they are or how they form or where they are or their properties as a function of wavelength. We actually don't know about the chemistry, like what are the kind of ratios of elemental abundances. There's a lot we don't know, actually. And so this problem and the inversion of it is really ill-posed. In exoplanets, it's not like Earth, where we can measure things in situ. Even solar system planets, spacecraft have gone there, and they have measured things in situ, so we have really no great anchor. Exoplanets, it's like disk averaged, and the whole column of the atmosphere over the whole disk is averaged literally into one point. So we don't have a lot of information. We have low signal-to-noise resolution, big degeneracy. Nonetheless, that still motivated the field, the community, to use retrieval as a natural way to quantify ranges of molecules and to gain a statistically robust framework to derive atmospheric properties. I'm disappointed to say in the end, like you can retrieve and say how much water vapor is in my atmosphere, and you still can't constrain it to more than a factor of a few to even a factor of 100. But we still impose this framework on it. And what I'm showing you here is data is in green, the points and the error bars, and magenta and red, they're just best fit models. And this is wavelength in microns. So the data's not that great, but you can still fit a model. All these wiggles here, they're molecules or atoms absorbing in the planet atmosphere. And again, the planet looks a little bigger when the atmosphere is in play. To explain retrieval to you really basically, the first way that my student and I approached retrieval, we hardly had any data back then, by the way. We'd have an observation that had 6 data points. So we did what we just simply called retrieval the million model approach. We wanted to generate, let's say, as many models, millions to billions of models that would fit the data. And we sort of fit every single model and ask which ones actually fit the data. And that's, really like a brute force approach to trying to solve this inverse problem. But it makes no sense because you can't generate 10 billion models. You need to use some foresight and guidance. So the field now uses a Bayesian framework to use priors to guide you through which solutions are necessary. But the solution space is still too huge. So we use Markov chain Monte Carlo or nested sampling or other things to help you walk through parameter space in a more clever way. And in the end, what you want to do is derive these posterior probability density functions. So I can't explain this whole graph to you. The point to take away is in this case, in this review article by Madhu Sudan, he is showing an example where he's just got 5 components. He literally only has 5 components that he's working through. And you can just sort of by eye see, at least these distributions are kind of tight. If they were like filling the whole box, it would not be retrieving anything useful. Now the temperature space here, he's trying to find a temperature profile from the base of the planet to the top of the atmosphere. It might look good to you, but if you look at these numbers here, for 2 sigma, it's going from 1500 to like I gotta read, see what this says. It's going from, I wanna say 1300 to 2900. You're really not constraining the temperature that well. The information is all blurred together. But I wanted you to know we still do atmospheric retrieval. Now in this retrieval, it sounds all great, and there's lots of people working on this. There's maybe like 5 groups, well, not lots, okay, in Exoplanets maybe, let's say 6 groups working on pioneering things. Actually, Julian DeWitt, who's talking tomorrow, he's one of the pioneers of this field. Now there's more and more people just adopting it. And just to explain it in a little more detail with this schematic, so we have data, that's our observed spectrum. We have our model, that's our model atmosphere. Then we have a parameter estimation scheme, so we can constrain the different components that we care about, like abundances and temperature. And then we can do stuff with it later. Now these models, because of the way we're marching through parameter space, like if you wanted to calculate a model properly, it could be like an hour per model. You can't do that because you got to calculate one each time. So we have a parametric representation. It's not really a real representation. I mean, it's real, but for example, the temperature and molecule distribution may be completely uncoupled from each other, where in reality, if the molecules are absorbing light, the temperature changes. So it's almost like, I don't want to say it's a dead end to begin with, but the method, the time that it takes, like the computing time, it's very compute intensive and very, you need thousands to millions of atmospheric models, and you want to find the most probable values and uncertainties associated with each model. And so you kind of run into a problem because it kind of scales with number of components. And there aren't just 5 components. Our atmosphere has like dozens of different molecules in it. Most of these models now, they're considering uniform distribution with temperature. That's actually not true in our atmosphere. Only some gases are uniformly mixed. So you have many, many, many more components you'd like to do. So this is really where the field is really ripe for major advancement. And people in astronomy just want to use machine learning, deep learning. It's like a tool. It's like, oh, I have a problem. I can use that for my solution. And so they've been sort of in a fog, moving to try to improve this. And one thing people did, for example, was they claim there's a lot of human bias in this field because how do I know which 5 components to choose? I chose water, H2O, methane, CH4. But how do I know that's right? Like if I gave you the problem, you don't work on atmospheres, which molecules would you choose? So some people have used machine learning in advance of doing this complicated retrieval problem, just to sort of figure out what molecules would be there. You could give it not just 5 components, but dozens, and let the machine learning sort through for you which molecules matter as input. But as I was preparing for this talk, and I'd known about this paper, it just came out, I think this is 2018, in Nature Astronomy, what could be like a real breakthrough in this field came out. And what these people did, first of all, here's the data, 1 to 1.6 microns. This got cut off its transit depth. And the blue is a model, and this again is the water vapor feature. They're saying that red is data, black is one of the fitting models. And they only have 13 points here in this data set. But what they did is they basically removed the entire estimation chain that I showed you of having to go back and forth between the parametric models and the estimation train. And they literally just used like a random forest adapted method of supervised learning applied to the data itself. Now, one way you could describe this is they have this sort of data in n-dimensional space, where n is the number of wavelength bands in each spectrum. And then they identify clusters in that multi-dimensional space. So model atmospheres belonging to the same cluster tend to share similar physical attributes. So when the trained machine is given like a real-life spectrum to analyze, it plots the spectrum and assigns it to the physical attributes to the nearest cluster. So kind of by moving away from this kind of statistical Bayesian framework with like MCMC or nested sampling, they're somehow allowing the training to not be as dependent on the number of components. And it actually is much, much more quickly. And I think it's really big. So I would put my money here for a deep learning or other things to get to this, help this field advance in terms of time. Now, one thing that's maybe a problem is that they have to simulate the training set, because look, we hardly have any atmospheres measured. I said it's a lot, it's like dozens, but that's not thousands. And in this work and other new ones that are more similar to it, they're computing like 80,000 models for their training set. But they may have some human bias in making those 80,000 molecules, because what you put into your model is what you get out. And so it's not clear kind of really where this is going yet. Also, I have to say, despite being so enthusiastic about this, it didn't do quite as well on the few things they tried it on as the more traditional way that people do retrieval. So these posterior distributions, they're like not quite as tight actually. So there's still a little things to work out, but I think it's going to be great. So today we use the Hubble Space Telescope to study hot giant planet atmospheres. And in the near future, we're going to have better and bigger telescopes coming online. And one of those is the James Webb Space Telescope, which we'll use to study small exoplanet atmospheres. So if you had this talk like 10 years from now, hopefully someone would come by and they'd give the talk not about a hot giant planet, but maybe, if lucky, even about a small rocky planet and its atmosphere. And so now that unleashes a whole other set of questions. Can we, can we like find signs that the planet might be able to host life or that it even does have life? And that will be the last part of my talk. But when we get into this concept of gases made by life, now our atmosphere problem, with all the problems, becomes way more problematic. Because giant planets, they have the gases they were born with. They don't evolve that much, whereas our own Earth, we're completely different than our atmosphere was initially. We think our atmosphere had a lot of hydrogen initially. Now it has oxygen after the rise of photosynthetic life. And so we have geoflux, we have volcanoes, we have life-producing gases, and then we have photochemistry, is that ultraviolet radiation from our sun reacts with the particles and kind of creates a cascade of chemical reactions that changes what you initially had coming out of the ground to something else. And so it becomes way, way more complicated. So I'm going to walk you through where we're at in the search for life on other planets. It's really a theoretical search in our computers right now. But it turns out that for literally over 80 years, 8 decades, people have been thinking about searching for oxygen on other planets. 80 years ago, they weren't thinking about exoplanets, but more like planets in our solar system, like Mars or maybe even Venus. Oxygen remains our best biosignature gas. It's so reactive, it shouldn't be in our atmosphere at all. So if there's like an intelligent civilization with the kind of telescopes we're trying to build, not too far from us, and they look at our Earth and they see oxygen, they'll be like, wow, that is just crazy. Why is there so, if they have retrieval or maybe they have deep learning, they'll know how much oxygen. And if they see that our atmosphere is 20% oxygen by volume, for us actually, without life and without photosynthetic bacteria and plants, we would have virtually no oxygen. We might have like 1 part in 10 billion oxygen. Instead, we have 20%. That's a lot. And so it should be continually produced, and hopefully these aliens, who hopefully they are looking back at us, they're thinking there's some kind of complex life here. Now, it turns out that they're in this field of astronomy now, as we get closer to when the day comes that we can observe these atmospheres, there's like this whole cottage industry now of people claiming, no, oxygen, there's so many false positives, and they come up with a scenario having to do with a variety of things I can't get into right now. And then a couple years later, someone will say, no, you didn't close your energy budget properly in your chemistry model. And so they kind of go back and forth. I think oxygen is still great. We won't know at the 100% level that there's life if we see oxygen, but it will be enough to kind of keep the next generation of the searches going on. But it turns out that there's lots of other gases. There's methane, nitrous oxide. There's other examples that life actually makes it as byproducts of microbial energy extraction. You may not know, but lying around on our Earth's surface, there are chemical potential energy gradients. And just like if you carry like a ball up an apartment building elevator and drop it off the top, you've done work to give the object potential energy. And when you release it, it gets kinetic energy. And there are literally similar things in the environment. There's chemical reactions that, when catalyzed by life, release energy. and they have chemical byproducts in the process. So life's like everywhere, exploiting these potential chemical energy gradients, and a byproduct is gases. So one example is methane, where life at the seafloor takes carbon dioxide that is mixed down from the atmosphere, and takes hydrogen that's been released from hot water pouring across rocks. And using those two together and catalyzing it, it gets energy and produces methane and also water vapor. But one unfortunate thing about that is to get over the energy barrier, when life catalyzes it, it's not a very big energy barrier. So the way I look at it is that somewhere else on the planet, that reaction is probably happening spontaneously. The temperature and pressure are different enough so that the reaction just happens. And that's true for methane production, because in our deep sea ocean ridges, it comes out of the ocean ridges. So that was a complicated way of saying that all of these gases here, they have false positives, because life can produce them, but life has the same molecules and gradients to work with that geology and geophysics does. So they'll also have that. It turns out that life on Earth produces thousands of molecules. It produces molecules for more complex reasons. Most are unspecified. Like one molecule astronomers got excited about is called dimethyl sulfide. It's produced by phytoplankton because of stress or signaling or some other reason. And life produces thousands of molecules, although most of them are available in tiny quantities. And in my group, we literally use combinatorics and other methods, and we've calculated every single molecule that will be in gas form at room temperature and pressure. And it populates chemical space, so we create algorithms to filter them. And our goal is to be prepared to search for and identify gases of any kind. Because it'd sure be a shame if in the future we go out, get telescopes, look at atmosphere, and see some things that we have no idea what they are. In the worst case scenario, miss our chance of spotting a gas that may be produced by life. So I have an example for you out of all these molecules, and it's a gas called isoprene. Now, you may not have heard of isoprene, but it's produced in tremendous quantities on Earth, as much as methane. It's made at like 500 teragrams per year. And in this plot here, it's showing you methane, isoprene, and a few other gases, nitrous oxide, methyl chloride, and just how much, just to show you it's huge, huge amounts of isoprene compared to other gases produced by life. It's a really interesting gas because it's produced by mostly trees and plants, but even we're breathing out isoprene when we breathe out. And it's been another curious fact about it is it's produced by nearly all branches of life make isoprene. It turns out it's somehow like a perfect chemical scaffolding to build more complex molecules. Now, I don't know if any of you have been to the Blue Ridge, it's called like the Blue Ridge Mountains in Virginia. It's somewhat obscure. But it turns out that isoprene is responsible for a blue haze that you sometimes see over forests. And the reason why on Earth we don't think about it as a biosignature gas, and why people who work on Earth's atmosphere just hate the idea of isoprene as being a life marker, is because it's immediately destroyed on our planet. It's completely destroyed by OH, radical, and oxygen, and it ends up being hazes that make forests look a bit blue sometimes. So we imagine that other planets, though, have other characteristics. Like they don't have oxygen, for example. Our own Earth didn't have oxygen for half of its life, in which case it wouldn't have much OH, and that this gas may accumulate. Now, it may be that this one really cool thing about isoprene, by the way, is it has no false positives. It cannot be made in a volcano. It actually is thermodynamically nearly impossible to make it, just kind of in the environment. And we can work out some basic thermodynamic equations to show that. And so it's kind of cool if you could see isoprene. It has no false positives. You'd be like, yeah, that could be a sign of life. Now, of course, the situation is way more complicated than that, and I can't have time to do it justice right now. But my team is literally trying to work through every gas possibility. There's a complicated flow chart. You don't have to understand it all, but essentially we have thousands of molecules. We want to know if they have spectra. We pump it through an atmosphere code. We ask, does it have spectral features that are worthwhile? If not, it gets dumped into the trash. If does, it can be evaluated further. We ask, can it survive atmospheric chemistry? If yes, it goes down here and so forth. Now, one of the problems is that we have this list of thousands of gases. But there are many properties of the gases that, as relates to atmospheres, are just not known. We only have spectral features like lineless or cross sections for a few hundred of these gases. Through thermodynamic properties, they don't exist for a large chunk of them. And when I was preparing for this talk, I came across this funny video here. Representation is everything. And this is showing you how hundreds of years ago, people believed that our Earth was the center of the universe, and that all the planets in the sun revolved around Earth. And because astronomers you can look at the night sky and see planets on a night-to-night basis. Like if you look out tonight, you'll see Jupiter and Venus. But a month or two later, Jupiter and Venus will be in a different place on the sky. So in order to be able to predict where planets will be at what time, because hundreds of years ago, astrology was like key. People had to have this very complicated model. They had epicycles on epicycles. Like you have the circle, and then you have these, and it actually worked pretty well for the data at the time. They could literally predict where it is. But then Copernicus, we got better data, and Copernicus came around, and Galileo was put under house arrest, and Bruni was burned at the stake for heretical views, partly that our Earth is not the center. Our sun is at the center of everything. And now look how much simpler the model is, although it's schematic. So representation is everything, especially when it comes to more sophisticated computer algorithms. And the problem we have in chemistry, or this problem here, we'd like to be able to, so the funny thing was one of my team members is like, well, let's use machine learning to get thermodynamic properties of all the rest of our molecules that we don't have it for. Somehow thinking it could be a magic bullet. But our problem in chemistry is representation. We have, there almost is no way to represent the complexity of electron clouds and how they interact with, there's no really great way to describe the way that electrons move around molecules and atoms in a way that lends itself to machine learning. This is like my own view, actually, because it turns out that you might naively think if you have a molecule, let's say you have this long molecule and the functional group at the end, or it's made up of functional groups, and another molecule is just made up of a different combination of functional groups. You might expect that if you understand part of the molecule, like Legos, you can put it together and understand different molecules. It turns out just the way that the electrons move around makes it too complicated to formulate any really basic description. And the one thing you're really after is what we call potential energy surface. Like imagine you have two atoms on a molecule. If they get really close to each other, they have repulsion. But if they get really far from each other, the molecule dissociates. You end up getting like a kind of parabola in potential energy space. But the details of that depend on the atoms and the electrons, and it's incredibly hard to calculate. So in this case, I don't have a solution here. I wanted to kind of pose it near the end of my talk as I really wish we could just kind of take this deep learning, and it's not an inverse problem or anything, but find a way to let the computer figure stuff out for us and magically help us out in starting to sift through thousands of molecules. So to summarize my talk, we have discovery. We have thousands of exoplanets known. The main way we find planets today, and I don't see Eric Ford here, but later in the conference, he'll be talking about a different way we find planets. But we use these large transit surveys. We look at thousands to tens of thousands to millions of stars. And I explained to you how humans work through these different metrics. And there's automation by various AI techniques is ongoing. I next talked about characterization, saying that exoplanet atmospheres encode more information about the planet. And that's the inverse problem I gave to you. It's very clouded by the fact that our observations have low signal to noise, low resolution, and it's like a disk average, atmosphere average information full of degeneracies. But this is where I think the inverse problem is ripe for further breakthroughs in AI. Search for life. It's like a huge thing we're all interested in, but we've got to solve some of our other problems first, finding small planets and characterizing the atmosphere. And here I walked you through a few examples, and I think that description of the molecular structure may be the key barrier.